the presentation we have in this session is team number 17, the calibration device for microarray slides. The customer is Professor Selim, Ünlü.
Hello everyone, thank you for coming. We are Team 17, calibration of microarray slides. My name is Lagoy, this is Allison, Marn, Sasha, Gazman, and Jyotsna, Singh. We are Microarray Calibration Inc.
Researchers are constantly trying to improve methods of detection. A common method of detection for viruses, allergens, and cancer is the ELISA test. The problem with the ELISA test is that it requires tens of microliters of solution, which requires drawing vials of blood, which can be uncomfortable for a patient. The alternative for allergy testing is a skin test. With a skin test, the doctor administers 50 pricks down the arm and waits for a reaction. This is not only physically visible, but a reaction can be very uncomfortable for a patient. The alternative method of detection would be to use a microarray. A microarray is a high-throughput testing method that uses only 10 to 100 microliters of solution. This is the equivalent to using a fingerprint prick of blood versus using a vial of blood. The example here shows a zoomed-in view of a microarray. Each of those spots is 100 microns in diameter, so it's very small, so you can fit many of these tests on a huge microscope slide. This example here circles regions and shows that each region tests for a different disease or virus, and there are multiple spots to detect for those so that there is more accuracy.
So, what is the problem with this? Well, microarrays usually have 3 steps for placing the sample onto the slide. 3 steps consist of layering 3 different types of biological masses. And what happens with the testing of microarray slides is that the third test, or a third biological substance is measured, but not any of the other steps. So what we're doing in this is measuring the first step to see if there's any difference. So what are we going to do?
To solve this problem, we have devised an automated calibration system that measures the amount of biomass deposited in the first layer shown in the microarray. This, in turn, improves the accuracy of diagnostic tests. As you can see, it's a compact and portable device. It is extremely user-friendly, and it's meant to be used by anyone who's not formally trained. By following 4 simple steps, by just loading the sample into the holder, opening the user interface on the user's laptop or computer, and following simple instructions that are displayed in the interface, and then finally analyzing the results that the software outputs. So to do this, our project consists of 4 main deliverables. The first is the physical optical system that collects all the images from the sample. Second is the LED control, which actually illuminates the optical path in the system. Third, the acquisition and analysis software. And fourth, the microarray slide.
Alright, so this is the block diagram top overview of the deliverables that we set up in this instrument. In the heart of our instrument is the optical system. All the systems are powered through a USB cord with one USB cord by using the 5 volts from a PC. The user input is starting the data acquisition in the software and inserting the biological slide into the device. And the output of our instrument is a spreadsheet that will tell the user the height of every spot corresponding to the slide.
As Sasha mentioned, the first step is to insert the slide. The slide holder holds a standard 75mm by 25mm slide. And it's simply inserted by lifting the lid, inserting the slide, closing the lever, and closing the lid. The slide holder sits at the top of the device for easy access from the user. They don't have to slide anything under an objective. Underneath the slide, you can see the camera at the bottom, and it is lit through the LEDs located on the left. The green arrows show custom alignment mechanisms that were developed to hold and align the optical system inside of our rigid enclosure.
Alright, so since one of the main deliverables in this project is to make our instrument automated, we designed a custom-made PCB board that serves as illumination source in our device. So the functionality of the PCB board is to provide a constant current to the high power LEDs, to toggle the LEDs, and to control their intensity. So in the PCB and the firm side, we implemented a UART communication between a PC and the microcontroller that we use. We're accepting different characters that govern the LED's control, and we're generating a pulse width modulation signal for adjusting the intensity. The table on the right, or on your right, shows the different characters input and their functionality. Alright, so this is the PCB layout. I'll go through the main components that we used here. We have a USB cord input. Then the data goes through a USB UART converter chip, FTDI chip. We're using an MSP430 as our microcontroller, and then we have four circuits that serve as the current source for the LED drivers. The LED that we're using is Accurate LED. They're operating at 350 milliamps.
So the device cycles through 4 LEDs during image acquisition. This is a histogram of the illumination created from each of those LEDs. Using the PWM signal from the PCB, each of the LEDs are modulated at 70% of the below capacity, as you can see here. They form a Gaussian located at 70%, which is what we expect.
So now we'll talk about the software. The software is what ties everything together, all the hardware. And so there are 4 main modules. We have the image acquisition, where it runs through 4 different LEDs and takes an image of them, of the illuminations. Then we have filtering, which filters the image for image processing. Then we have an image detection algorithm that is implemented. And then finally, we have a reflectance curve matching algorithm that is used on the GPU and computed pretty quickly. So this is a graphical user interface that you would see when you're using the software. We have a instructions box. We also have an image box which shows all of the current images and all the filtering that's occurring in the software. There's also a status bar so that when there are computations done in the back end, you'll be able to see that the software is actually working. Also, you can see that there are 2 tabs. There's a control tab and an advanced tab. The control tab is what you'd use on a daily basis if you're using the software. The advanced tab is for more advanced users, and I won't go into that right now. So we have data acquisition. Data acquisition is where we take the images from the camera and we change the LEDs so that we can get a different image for each illumination. We take multiple images for the LEDs. We average those images together to reduce the camera noise. And then we also added a feature where we can select the area of interest. And you can see it with the red outline on the screen. This is used as a way to add heuristics to the spot detection algorithm. There are 4 different images on the screen right now. These are the different steps within the filter being used. We have A, the original image, B, the image after equalizing the histogram, C, we subtract the background using thresholding, so we look at a threshold value, and then if the pixel meets a certain threshold value, then we subtract the background and consider that a white spot. And then lastly, we have a median filter, which eliminates some of the noise that exists in the image. After applying the how transform, which is implemented in the OpenCV library, we use MGU, which is a C# wrapper for the how transform, or the CV library. We're able to detect all of these spots pretty accurately, up to 90%. And we're able to sort the spots in a certain order from the top left to the bottom right, and then it was saved into a file where the user would be able to access this later on. Then, for the nonlinear fitting algorithm, this is used to calculate how much sample you have on the microarray slide per spot. So we use 11-Berg-Marquette fitting algorithm. It optimizes a way to figure out the heights based on the pixel values. It's highly parallelizable. So we were able to use CUDA, and it was developed by a master's student in the lab. It reduces the computation time from greater than 40 minutes on a cluster of computers to less than 2 minutes on a single laptop computer with a GPU. This saves useful data in a CSV file so that the users will be able to use it in the future. to see what the signal height is, or the spot height.
So to validate our device, we compared our results with IRIS, which is a biomass measurement device that's been verified to give accurate height measurements. And you can see our measurements are plotted on the x-axis, and the IRIS measurements for the same spots were plotted on the y-axis. And a strong correlation shows that the results from our system are indeed accurate and all of what we would expect to see.
Now I'll talk about the final deliverable of our project, which is a new design for the microarray slide. On the left, the image shows the current slide design used in the lab. It's an opaque, two-layered design, which is a few silica on silicon. And on the right shows the new fabricated design. The purpose of this slide is to be transparent because several diagnostic labs use transmission fluorescence imaging, which is another qualitative form of measurement for imaging. To enable our user both qualitative and quantitative analysis, we have devised a transparent slide that can be used for both purposes. The image up top shows a cross-sectional view of our proposed model, which is a three-layered stack of silicon nitride sandwiched between two layers of fused silica. We divided this model through the electromagnetic modeling of several transparent reflective materials and several over different layer thicknesses as well. And the image on the right again shows the fabricated version of our model. We collected some data on verified instruments such as the IRIS that we use in the lab. And the image on the left shows microarrays plotted in our transparent slide, and we can see that the spots are visible and they're measurable. Further analyzing the reflectance response over the 4 LED wavelengths, we can compare the model-generated results with the experiment. And the model-generated results do show a strong prediction of the trend that we observe in real life. There is a DC offset that does need to be further investigated.
All right, so this is our budget distribution. The total cost of our device was a little bit more than $3,000. However, if this device will go commercially, we'll be able to decrease this price dramatically.
So in conclusion, we have a highly automated device that will require at most 5 clicks for a user to analyze the data. We also have a new slide design, which can be compatible with other imaging modalities, including transmission fluorescence. It's cheaper, faster, and smaller. It's cheaper because it uses least expensive components. It's faster because we use CUDA, which is on the GPU, for computation. And it's smaller because it's compact and portable. Overall, we are increasing the accuracy of diagnostics.
We'd like to thank Professor Key and Professor Pisano for their endless support and encouragement, our customer, Professor Selim, Ünlü, and the entire OCN lab for coming and supporting us, and for their guidance throughout the 2 semesters. And last but not the least, Mr. Howard Cohen, the VLSI lab manager.
This is some of the technology we used in the project. Is very interdisciplinary. As you can see, we have a BME and double E's on this team, so we had to work together to form a solution to a interdisciplinary problem.
I'd like to open the floor to any questions.
You mentioned, LM algorithm, the 11-verse algorithm.
Yes.
There's sophisticated technique for the first system. So, did you use MATLAB for doing that? Did you understand exactly what the data does and so forth?
Sure. I actually didn't implement it. It was done through the master's student, and also prior code that was written. But it was all done in C++. So it wasn't something that I've done, but I had to modify mostly the CUDA code and also some of the binary communication, or the binary files that communicate with my my GUI and front end and the CUDA as well.
You have such a multidisciplinary project that really touches upon a lot of the stuff that we teach here. optics, mechanical engineering, electrical engineering. So I'm wondering, just out of curiosity, what did you find to be the most challenging aspect of this project?
I think integration, just because each component on its own could be executed and executed well, but I think combining all of these very distinct disciplines was a challenge, especially towards the end.
Yeah, and because we're working with optics, which can be very finicky, you can move something very, like at a small distance, and it would change everything. The illumination wouldn't be as good as what you can see in those MATLAB plots. Also, I think, definitely integration was the hardest part in the project, but all the mechanical design, since we're doubly in BME, this was all designed custom. We got it sent out. The slide builder was done by us. So just everything in general, but integration was definitely where we saw most challenges over the past 2 weeks.
I actually have 2 questions. So it's portable, right? Are you worried, just like you said, optics and things like that alignment, are you worried about vibrations and what's going on with the
So everything is bolted pretty securely. We haven't tested for major vibrations, but we've done testing on normal tabletops that can get bumped, shaken, and moved on, and we've still been able to achieve good results.
Okay. We'll be able to actually demo the equipment after this, and we've been carrying it around all day, so you'll be able to see that we're able to get some pretty accurate spot heights.
I also have a question about your spot detection. So you said you use the off-train spot.
Yeah.
So is the user within, I'm vaguely familiar with those.
Yes.
Does the user put in the number of spots and then it's trying to pick out that number of peaks in this transform?
Yeah, so it has a probability space where it chooses the most likely areas for spots. There are some parameters where you're looking for contrast differences.
Yeah.
But across all the images that I've been using, there's a pretty, well, especially after doing the filtering with the equalizing, the histogram, and also the median filter, I was able to detect pretty accurately across all different images.
What about, does it have problems with spots that are not uniform? Because I know with the spotting techniques you'll get.
Yeah.
What does it do with those?
All right, so either it won't detect them, and we also have included in the software, which we didn't talk about, but we have a standard deviation over mean of all of the heights calculated, which tells you a little bit about morphology. And if the standard deviation is varying or very large, then you'll be able to know that your spot isn't the best that it could be. So there's kind of a rating for the spots. It hasn't been fully implemented, but we do have the standard deviation for the user to look at. Yes.
So, your presentation is sort of step 1 of the process for how do you see this impacting the further steps? Is it a pass-fail on a spot-by-spot basis, or do you think you can pass-fail on an entire slide basis?
So we measured that.
So we're measuring the initial concentration, and it just helps kind of qualify the end result. So the user measures the end result, but they want to correlate it to something. If they're getting a certain signal, they want to know how much that signal relates to. So, so in terms of microarray testing, it kind of, well, this is our spot-by-spot correlation. In terms of microarray testing, right now, you're getting a qualitative answer at the end, you're getting a yes or no. But with our device, you'll be able to say how good of a yes, how good of a no. And it's really good for allergen testing for a certain threshold, because giving a yes or a no is very easy to have false positives, but if you know how much of a yes or how much of a no, it kind of gives you more of a context.
Of how severe something might be. So it gives you some other dimension to this problem.
I was thinking more if, for example, you see one line response in place, right?
Yeah.
Are you going to throw an entire slide with the data because you've seen something wrong, or is this going to be more of a
Spot by spot.
You can turn these off and ignore that data?
Yeah, because the software outputs a actual diagram of all the spots and numbers them and shows you the results towards their number. If you see that a row just didn't spot well, something went wrong, you can just ignore that row and you know that that's not good data that you can take into account.
Yes.
Does MicroCal versus Iris depend on the new microscope slide?
No, was imaged on the old microscope slide. The new microscope slide has not yet been integrated because of that DC offset. We aren't able to get pure, accurate results. This was done on the old substrate, which was a silicon oxide on silicon.
Okay, so basically, standard microscope slides work in your device.
No.
I mean, the code, it's regular 25 by 75,
Yeah,
not a triple layer,
Yeah.
quartz and what have you.
They're, right now, our device works with dual layer interferometric slides.
Yeah. So they have to have that property, otherwise there's no interference.
Right, no, I understand.
Yeah,
I mean, it doesn't depend on yet a new technology for the consumable, for the device
Right.
to work.
Yes.
Right.
Okay.
Yes.
In your spot detection, there's no image processing algorithm that works on any data. So you have some tuning parameters.
Right.
Did you kind of test how tuning, you have your histogram equalization, you do intermediate filtering. Did you test how parameters of those steps affect your precision?
So not specifically. However, we did have to, the only things that we had to address we had to change for the variables were in the how transform. Because we had to choose a threshold value. And that threshold value was similar across the board for all the images. So the main error is in the how transform, but because we're normalizing all of the pixels by a mirror scan, we're able to take out gradients, and it levels out almost all of the image and takes out a lot of
But
noise.
in histogram equalization, you need also binning, and in median filter, you need to have the median size.
Yes. All right. So median size is it's a very small size. It's a 3 by 3, so it's not very large. It just takes out some of the extraneous like pixels that might exist. Yes.
You showed that your system appears to be as accurate as Iris.
Yes.
So if you were to compare Iris versus your system, what are some of the advantages of your system versus Iris?
So the main draw of our system is that it's compact, portable, and it's not, the Iris is only in a lab setting right now, bolted to a floating table. It's not very versatile.
Also, it's much faster, and it's automatic. All you have to do is click 5 buttons, and it's done.
You're talking about a fairly elaborate laboratory setting
Yep.
for Iris versus a small, compact, portable, easy-to-use device.
Also, the current setup requires aligning the sample, shifting and focusing, and doing all those different steps, figuring out which exposure time you want, like very different variables. In this, everything is automated, predetermined.
The slide holder is what's key. Before you're just poking at it with a pair of tweezers, trying to get it underneath the light. But with this, just slide it in, and it's right there, and you can do all the detection.
Is your customer planning to throw away Iris and use your devices?
Hopefully.
They promised they wouldn't go to the trash.
All right, thank you.